Hello, today I'm going to talk about various techniques of numerical approach of partial derivative equation. In France we call it EDP, équation au dérivé partiel. So at first, what is an EDP? So you have a linear system that is a times y plus b times the derivative of y over t plus etc. plus z being the nth derivative of y over tn. But when you have various variables, you have the partial sum over t, but also the partial sum over x, and then the crossed, the dérivé croisé in French, the crossed derivative of y, so one derivative over t and one derivative over x. So this is a general definition. So we're going to talk about various conditions. So usually we talk about condition of Dirichlet. I'm not sure about how it should be pronounced. So we define a small area inside the space in which x is defined. So usually the boundaries. So, but it can also be any area in the middle. If you say that on the left side the temperature should be a fixed one over all values of t, then it would be this condition, because at some point, at a point of space, you'll have a specific function that will be a constant. So g of d will be a constant temperature in all the values that are on the boundaries. So this is called Dirichlet condition, and it can also be applied in time. I'm not sure about how you call it, but usually you call it a position condition, because it's a condition on the variable itself in t equals 0. So if it's a mechanical problem, the solution actually is a position, so we call it position. And even when it's not a position, like temperature, we call it position anyway. So now the condition of Neumann, yeah. So on the same boundary, so it's a space inside the space of our study. For values of t, the derivative over space is equal to a certain value, a certain function, but usually we take a constant. But it can be a cosinus, for example. It can be like, I know on the left I will have a temperature that is equal to cosine t, sorry. And the same thing for time. We call it a speed condition, but even if it's not speed, it doesn't matter. There is also a condition called a condition of Robin. I'm not sure exactly how it works. I just heard about it, so I'm just going to drop it here. But it's sum of the vector plus some derivative of y over x. Yeah, derivative over x, yes. So there are three known methods. There is the finite differences method, méthode des différences finies en français, in French. This is the one we'll deal with. The finite elements method, méthode des éléments finis. Basically, it means that I'm not sure I will not try to explain it. Same for finite volumes method, method of finite volume. Basically, this will use various techniques of integrations. They are ordered in strength. So the volumes is the most powerful one. Elements is slightly weaker, and differences method is weaker, but differences is fine for one-dimensional problems. Elements for two-dimensional, and volumes for 3D, which is why in 3D, so in engineering, we usually deal with full finite volumes methods if we are dealing with 3D problems. but a simple approach can be differences method. Very rarely cases when you have to deal with elements, but if you are dealing with a software, it might 99%. I'm 99% sure it uses finite volumes method. So now we will build an operator called f of h, and we say that it's a consistent approximation of order p of the kth derivative of phi if there exists a c constant, if the maximum over all the variables that it takes of f of h of phi minus the case derivative of phi is inferior to c to the power to c times h to the power p, meaning that uh, f is equal to the kth derivative of phi plus O of h to the power p, so the O of Landau. Now we build switch operators like this one, so the progressive one being the phi at x plus h at x plus h minus phi at x over h, so it's a order one approximation of phi. It takes the following value minus the current value, so it's progressive. And for regressive method, it's pretty much the same, but you take the current minus the previous one. And there is a centered one. I'm not sure how to spell that word exactly. So it's 1 over 2h of the following value minus the previous one. You can find easily these values with the theorem of Taylor. So you apply the theorem of Taylor in f of x plus h, you apply it in f of x minus h, and you linearly sum the variables, and yeah, you get those results. So an example in 1D. So we take this equation here, and we use our operator. So we replace the derivative here. We use the d d of u. So it's a composition of operators. So we will get this this value. So x at u at the following moment, at the following place, minus twice the current times minus the previous one over h squared is a approximation of second order because h equal to. So we call ui being u at x at xy. So here we have a problem in space, but it doesn't really matter for 1D if it's space or time or whatever. So we replace in this equation. So the part minus the second derivative of u comes here, so this we factorize here. The 2 comes from this part, plus ch squared. Ch squared comes from the fact that we have c here, and we divide by h squared, so we put it in to a whole fraction. And this thing here is the same thing as here because of the fraction. That is equal to a certain function if we search for the precise solution, so f of x plus O of h squared, but we will forget about the h squared, and we call mu to be equal to 2 plus ch squared, and also we multiply by h squared in both sides of equality. In the equality, we get this, and we will forget about the OH squared part. So the initial condition, we have O of x0 to to be equal to alpha, so certain value alpha, like the temperature at at the left side is equal to 0 degrees Celsius, and the right part is equal to 10 degrees Celsius, and you compute the heat equation and whatever. So we get a system of equation. So u0 to be equal to alpha, un to be equal to beta, and with all the equations we've set earlier, for all the values that aren't in the boundary, we get this thingy here, and we get n equation with n unknowns, and if there is no special thing that can happen, so like trivial solution or impossibility of solving, this will always have a unique solution, so you can compute it by computing the determinant of the function. So we will build a matrix system. So here we have our boundary conditions here on the top left and bottom right, and in the middle we have our system of equations that are from the differential equations, and we get this system here. By convention we call this part A, so it's a matrix. Here is our vector of unknowns that we don't know and we want to know what they are, and this is our second term, so boundary condition and function that are in the differential equation. So now we will build A. So in our algorithm we will build A, we will build B, and we'll just do the MATLAB inversion. So U is equal to A backslash B, and it will compute the matrix division. So it's not really a division, but it computes it with using the Gauss algorithm and other method to make it fast. So I think the LU computation or something like that. Sorry, something I didn't mention in this when I wrote this is that you can notice that the matrix is called tridiagonal, meaning that the only the diagonal, the top the diagonal and the terms that are below and above are non-zero. So there is a function in MATLAB called tridiag. So look at in the help of MATLAB called tridiag. Basically, it stores this matrix as a vectors as three vectors. So the bottom, the middle, and the top as vectors, and it stores it. And when it does this computation, it doesn't calculate all of these zeros, it avoids them. So it can be interesting for COMSI people to use a tridiag to compute faster, but this also works. Also, now we can use different boundary conditions. What if at the n, so like the right part, if we are going from left to right, so n is the latest value, so the value at the right, if we don't want a fixed temperature but a fixed flow, so a fixed derivative of the temperature, we have to approximate the derivative of t. So we use various methods. You can find this approximation here. It's once again you have to use the theorem of Taylor, compute it in f equals x minus h and x minus 2h, and you have to sum it. So, and you get this result here. It's not hard, and you can change those conditions and you have this. So now you don't get a tridiagonal matrix, but it can be interesting to compute it at 3 diagonal and then just add this term here. 2 dimensions. So now now we imagine that we have two variables, a variable of time and a variable of space. So now we can also write our problems as a function like this, but two things will occur. A and B will be functions of time, so you have to recompute them every time. So you have to have a loop over each values of time. And initial condition can be hard to define. So I know that it's easy if you have the set of temperature at t equals 0 for all the space and the sets of variables on the left and on the right. But it can be very hard problem when you have the difference of temperature at a certain time. It can be quite hard to compute. So initial conditions can be hard to define. So now we have a problem, which is that there is also we have differentiation over time and differentiation over space. So there are terms of previous space that will inherently be added to the expression. So you have also to compute in terms of u at a previous time. But since we are computing at each time, we are iterating the process at fixed time over time. So this process is at fixed time. We have various variable of space, and we had time. It means that in this part we'll have values that depends on the previous values of time. So in an example here, here on the top we have a condition on the derivative on the top. Here we have different constant that I will not detail, but you can find it depending on your equation by using the method I detailed earlier. So like this, you have your equation, you have your approximation, you just factorize and you get all your constants. So you always have to express your you have always to this one. So you have always to express the part of your vector here as all the unknowns at the time n, so not n plus 1, not n minus 1, as a function. So the product with the matrix and the unknown vectors must be the values of u at a previous time. And also we had plus the discretization delta t. So it was h in our previous example. It was h in our it was h at our previous examples, but there is also discretization over x, as we can see on the derivative in the top condition. So we get this system here, and we have beta. So once again we have to iterate. So we build all the values of u at t equals 0, if we can, depending on the initial conditions. We build all the values on the left side, on the right side, if we can, obviously. And you can build this kind of matrix. And once again, you have to iterate. So you have to rebuild A. Well, not in this case. In this case, A doesn't depend of time, but B does. So you have to recompute B every time and do the matrix inversion as we said here. And you get all the vectors for all space. So each vector is for all space, and since you've iterated over time, you get a matrix that represents all the values over space in 1D over all the space in 2D. Also, I'll had to add that you can extend it to 3 dimension with 2 dimension of space and 1 dimension of time. And I'm not going to detail it, but it looks like a matrix with block matrices, and this whole matrix is a block, and you have on the diagonal all this matrix here. This is the diagonal matrix here, and on the terms that on diagonal depends on the other values of space, and yeah, you can compute it using this method, but in this vector you have to use uh, 2 dimensions. So if you have x values of on a certain axis and y values on another axis for the 2 dimension of space, so you have u00, u01, u02, u0 over u0x, then it will be u1x, u10, u1 blah 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 until u1x, and then so it means that this vector will contains y times x values, because you'll have all the variables of space inserted in a certain vector, and you can also apply this. And obviously you can extend it to 3 dimensions, but I have not seen it, but I think it's possible. And yeah, that's it for this. If you have any question, feel free to ask them in the comments. And bye.